So now that we've talked about the structure and functionality and key methods in Java ReentrantReadWriteLock, let's take a look at an interesting example application of this lock. And we're going to do this in the context of a simple implementation of the AtomicLong feature that you would find with Java Atomics. So the so-called SimpleAtomicLong class shows how to write a program using ReentrantReadWriteLock. And what we're going to do here is do something that's going to demonstrate the feature, although this, of course, is actually not how things work under the hood with the actual Java AtomicLong class. If you take a look at the real Java AtomicLong class, which we've looked at in earlier videos, you'll see that under the hood it uses atomic compare and swap operations. But we'll ignore that for now and take a look at how to implement it with a reader's writer lock. So that we have a value here, which is the current count of the simple atomic long. And as we'll see, it's going to be written to and read from, but is in fact not atomic by default. So as you can see here, a long without having it be volatile or something is actually not going to be atomic. Reading and writing to longs are not atomic, as you can see at the link at the bottom of the slide. So we're going to have to protect it some way. You might think, oh, well, let's go ahead and use a volatile here. We're not going to be using volatile because we're going to be doing reader's writer semantics to it, whereas volatile doesn't know anything about the difference between a reader and a writer. So to do this, we're going to go ahead and define a field, which is going to be our ReentrantReadWriteLock, and we're going to make a new ReentrantReadWriteLock. And this particular capability will be used to serialize all the access to M value, depending on what operation is being called. There's no need to use fair lock semantics here. We're not concerned with fairness. We're concerned with performance. The constructor goes ahead and initializes the M value to whatever the initial value is. And again, as always, remember, constructors are only called in one thread of control, so there's no need to worry about synchronizing them. Here's the increment and get method. So if you take a look at an atomic long, you know it has increment and get, which will atomically increment the value of the atomic long and then return the incremented value. So it's going to work atomically. And because we're changing the state, then we need to make sure that we use a write lock for this. So what we do is we say MRW lock, which is our field, write lock. So we get the write lock field from the ReentrantReadWriteLock, and then we lock it. And then with that lock being held in an exclusive mode, because that's what a write lock does, we go ahead and we increment the value by 1 and we return the incremented value. Note that this particular implementation is so-called pessimistic, since it assumes contention will occur. So therefore, no other thread can acquire the lock while the write lock holds the lock. Any other writers will be queued, any other readers will be queued. So that means that a write lock is a so-called exclusive lock. So it's a pessimistic lock. And as always, on the way out here, we use the try finally idiom to make sure that we unlock the write lock. Now, again, we're not going to get an exception thrown by incrementing the count by 1 unless we forgot. I think under no circumstances will we get an exception there. However, it's just a good habit to get into to write your code using try finally blocks, because at some point you'll forget and put something else in there, like a log statement or whatever, and then your code will throw an exception and the lock will not be released. Here's the get method. This method is designed to read the value of M value atomically. So once again, we need to make sure it's protected from other write locks that might be coming along and trying to modify the value of M value. But if we have lots of various threads that are only reading, we want them to all be able to go in parallel. So we implement that by using the read lock. So we say mrwlock.readLock. We get the read lock field. We lock that for reading, which may need to block, of course, if there's already somebody who owns the lock for writing. But if there are only other reader locks, then there's no problem. They'll all be able to go in parallel. And then we simply return the current value. This is also a pessimistic lock. It assumes that contention may occur with write locks, so we have to grab a lock. But if you have multiple reader locks at the same time, then there's really no locking overhead or no penalty for that. They can all, or not much penalty, they can all proceed in parallel. And as before, we use the try finally idiom to unlock the read lock on the way out of the get method. Here's another example, just for fun, illustrating the so-called lock downgrading functionality. So this particular example is going to use get and increment. So remember what get and increment does is it first reads the value and then it increments it and it returns the previous value before it was incremented. So to do this, we're first going to obtain a write lock and we're going to acquire that lock. And then with the write lock held, we're going to increment the value. So that was done atomically. And now what we're going to do is we're going to go ahead and get a read lock. And what this is going to do is this is going to downgrade the write lock to a read lock. So with that lock, we're going to go ahead and unlock the lock. So we unlock the write lock and read the value with the read lock still held. So what this means in practice is that if there are multiple threads that are now coming through to read the value, like doing get calls, for example, they can all proceed at this point. But anybody who comes along to do an increment or a change to the value is going to have to wait. So we've downgraded the lock from being exclusive to being shared. And then we go ahead and read the value of the M value. We read its value, which will be one more than we actually want here. We then go ahead and release the locks appropriately. And then the last thing we do here is we return the original value before we incremented it. And the way we do that is just by subtracting 1 from the value. And there's no need to lock value here since lock is defined to be a local variable inside the get and increment method. So since it's local to the activation record of the thread stack, then we never have to worry about any contention occurring because it's private at that point to that thread. So that's a lock downgrading example. I think you'll probably agree with me that this is fairly complicated and in practice probably not worth the effort, but I wanted to show you how you could use lock downgrading with a ReentrantReadWriteLock. So this particular approach is undoubtedly overkill for the SimpleAtomicLong, but it was an example that was meaningful and it demonstrates the concept of lock downgrading. Note that ReentrantReadWriteLocks do not support atomic lock upgrading, only atomic lock downgrading using this particular idiom. So that's the end of our example application demonstrating how Java ReentrantReadWriteLock works. And what we'll do now, of course, is we'll have the last part of this lesson evaluate the pros and cons of this particular class in Java.